Hey ladies and gentlemen, Mr. Mitchell here. I'm going to go over today's two notes with you, 3.2a and 3.2b. So first of all, here with 3.2a, the motions of the Earth, moons, and planets. So first of all, the Earth, it undergoes two different types of movement. The first is rotation. And rotation, as you can see on the picture here, is, if you can imagine this axis, kind of like a imaginary pole going through the Earth spins around that. So that's a rotation. It does rotate from west to east, and that's why the sun appears, even though the sun's not moving, the sun appears to move. The sun appears to rise in the east through the day, travel over top of us, and then set in the west. And that's because we are rotating in relation to the sun. The Earth rotates every 24 hours, so in one 24-hour period, the Earth will go around once. And of course, when we are facing the sun, it's daytime. When we are away from the sun in our rotation, it is nighttime. The second movement that we do is revolution, and this is the orbit, this green path here around the sun. It takes 365 and a quarter days. Our Earth's path, the orbit, is not a perfect circle, it's called an ellipse, so it's a little bit elongated. If you take the average distance we are away from the sun, we call that the orbital radius. This 365 and a quarter days is important as well, and we'll get to that a little bit later. The motions of the moon. The moon, like the Earth, also has two different movements. It rotates on an axis, and this takes about 30 days. So the Earth spins one complete rotation in 24 hours. The moon rotates on its axis a lot slower. It takes about 30 days. It also orbits around the Earth. It revolves, and that takes 30 days as well. Because both the rotation and revolution of the moon is both 30 days, we only ever see one side of the moon. That's right, every time you looked at the moon, you've only ever seen one side of it. You've never seen the back side. Now the Earth has a tilt, and you can see here that it's not straight up and down the axis. It's actually at a 23.5 degree angle. And this causes different seasons. If we go back to this diagram here, the Earth in the northern hemisphere, so you can see the equator here, and Whitby is up here in the northern hemisphere. In our northern hemisphere, we're actually 5 million kilometers closer to the sun than we are in the summertime. So you may say, well, if we're 5 million kilometers closer to the sun, why are we colder? Why is it winter? You think it would be hotter. And the answer is the tilt. Right here, this is winter time up here in Whitby, Ontario. And you can see we're tilted away from the sun. If you can imagine shining a flashlight on the table from a very low angle, when the light hits your table, it's going to be spread out over a great area. That's the same thing that's happening with the sun's rays. Because we're tilted away, the sun's rays and its heat energy is spread out over a great area, and so we have winter. It's a lot colder. If you move around to this position here, even though we're further away, we're tilted toward the sun. That's kind of like holding that flashlight perpendicular, straight up and down from your table and shining it. And you can see all the light that comes out of that flashlight it's concentrated into a little circle. And that's why we have summertime. The sun's heat energy is concentrated on us, and it keeps us much warmer. So right here, this would be your winter time. This here would be summertime. This position here is springtime, when we're neither tilted away or toward the sun, and over here in the fall. These two positions are called equinoxes, equal amount of daylight and darkness, but 12 hours of each. And these are solstices, the winter solstice and the summer solstice. So the seasons are caused by the tilt, and I've already explained that to you. As we are leaning away from the sun, tilted away from the sun, it's wintertime, the sun's energy is spread out, and in summertime we're tilted towards it. Now, eclipses. Eclipses are astronomical events that occur when something is blocked by something else. So in solar eclipse, this is where the moon blocks the sun. So here is the sun, here's the moon, here's us, and right here, this spot on Earth would be experiencing a solar eclipse. They would not see the sun because the moon has moved in between the two. And these usually only happen for a few minutes. Likewise, we have lunar eclipses, and this is where the Earth blocks the sun's light. So the moon has gotten in behind the Earth, it's in its shadow, and the moon appears to go dark. And once again, this only happens for a couple minutes. The moon is constantly in motion, as is the Earth, so the moon will get into our shadow for a couple minutes, but then it'll move out of our shadow and we can see it again. And tides. The moon is actually what causes tides. So tides are where the water level rises, and then when it's not tidal, the water level drops back down again. This is caused by the moon's gravitational pull. It'll pull on the water of the Earth, and you can see that the side closest to the moon and the side on the opposite side, furthest from the moon, will experience high tides, and these two adjacent sides will be a low tide. Now on to note 3.2b, interactions of the Earth and the Sun. So if the Earth's orbit brought us much closer to the sun, our planet might be lifeless, scorched desert. And if we're any further away, we'd be frigid and icy. We on Earth are in a sweet spot. So any closer to the sun, we would be scorched and burnt, to be too hot. Any further away, we would be too cold to grow any food and to live as well. So we are in a sweet spot. We call that the Goldilocks zone. And to protect ourselves from the Earth's energy, we have something that all other planets don't have as well. We have an atmosphere. The atmosphere, it acts like a big blanket. It keeps us from getting too hot, and it keeps us from getting too cold. It contains oxygen as well that we can breathe in, and it's also like the Earth's sunscreen. So it contains ozone, and it helps block out the sun's UV rays. The magnetosphere, we also have an invisible field of magnetic force that surrounds our planet called the magnetosphere. And it deflects solar winds coming from the sun and prevents it from entering the atmosphere. Some of this energy does enter, but at the poles, and it creates what is called an aurora. So some of you may be familiar with the Northern Lights, otherwise known as the Aurora Borealis. This occurs in the Northern Hemisphere, closer you get to the Northern Pole. And it also happens in the Southern Hemisphere, down by the Southern Pole, and is called the Aurora Australis. So the atmosphere is a good thing, but too much is not. So the sun emits forms of energy that are harmful to living things. And these include UV ultraviolet rays, and it's these UV rays that burn us, burn our skin. Ozone and other gases interact with this incoming energy and helps shield us from it. The atmosphere also helps trap some heat so that we stay warm enough to live and to grow plants. And it keeps us right at the right temperature. And it helps keeps us from experiencing too high of highs and too low of lows. So it moderates these fluctuations and keeps our highs and our lows closer together. And Earth is the only planet that we know that has these unique combinations.